What's up, everybody? I need to go now into Ankbot and remove the command that I just added, so just give me a quick What? This is a command? Look at this command that I have. How was this added? That's the command. I don't know how that was added. I also have this as a command. Why? I don't know. Sorry. Hey everybody, what's up? I guess I need to fix Ankbot because apparently I'd added commands that I don't need. I don't know when or how those were added. Oh, that's fine, Beardless. Again, it's all about the implication of what the answer means, and it's easy to follow along even if you haven't done math in a while to understand what I need that music in my life. Yeah, it's a cool playlist, isn't it, Demonata? What's up, everybody? Let me remove these obnoxious commands. Okay. Okay, that's good. And then, yeah, okay, cool, that's good. Let me get Ankbot back into its rightful location. And let me go grab my tea. You know what we really need? We need, like, a tea time. Tea time for the first 5 minutes while I'm getting everything set up. I mean, we kind of already do it, so... So maybe I should just, yeah, maybe I'll start doing that. Why not? Why not? Anyway, let me go grab my tea real quick, get my notes up, one note. Oh, you know what? I never, uploaded, yeah. File, export as PDF. What I'm doing right now is I'm exporting, documents, I'm exporting my notes from the last class. Save. Okay, notes are exported from the last class, so on the Google Drive. Puer? Puer? What's that? Did I say something that I didn't mean to say? I don't know. What happened? What happened? Okay, and then I'm gonna export these notes. So the notes from last class are now in the Google Drive, and I'm exporting an extra note, which is calculating the required altitude of a geostationary orbit. So with a specific planet, what altitude do you need to be at? Aged T? Cool. Yeah, I just do Lipton green. Calculating the required altitude of a geostationary orbit around any celestial body, and I'm uploading that into the extras folder. Okay. Fearless, I'm trying to get the word out, man. That again, Fearless, I'm part of a team called Twitch EDU, and we're actively trying to get more people involved in educational content on Twitch. I guess I should just put AERO 101 a little bit higher up on the panels, maybe? I don't know. Let me go grab my tea real quick. Alright, so let me open up a new page. Man, I'm having a lot of fun, by the way, with messing with the IVA cockpit in Kerbal Space Program. That's a lot of fun. Being able to manipulate your own ascent trajectory and whatever in-space burns you have to do right from the cockpit, that is awesome. Yeah, Beardless, I don't know. I try to keep it minimalistic as possible when it comes to, like, extra stuff like that. Like, I have, like, this space heist thing that you can do and all of these extra... I have currency and all this stuff that, honestly, I'm probably gonna do away with now. I don't know. I don't like the idea of having bots constantly bombarding the chat, right? I want the chat to be interactive. I want the chat to be a place where people can discuss ideas and discuss things that I'm doing without having to have all of these extra things pop up. But yeah, I mean, that's definitely a possibility to maybe make a timer. Okay. Let's go like this. Like this, 004. This is lesson 4. I said it was lesson 4 last time, but it wasn't. It was lesson 3. So sorry. This is lesson 4. Deriving Vis Viva. Okay. True. Okay. Let's go like this. Turn the music down for you guys, and turn the music down for me. Alright, I need to move this. I need to move this. I've got limited space to move things right now. Desk is a little cluttered. That's okay. Alright, let me get out my space tablet. Oh boy. Alright. Alright, space tablet achieved. Yeah, I really need to get like a I really need... What is this? I need to get some sort of protector for the screen here. Anyway. Alright, let's get to work, guys. What shall we? Alright, today, again, we're going over deriving the Vis Viva equation. We've derived Vis Viva before, but just in a different manner. And we're going to try to make it a little bit more consistent as to what we do, okay? Okay. Let's see here. So this is the real lesson 004, so sorry about that. Probably confused a lot of you guys. So we've got a general sequence, right, that we've been using to calculate these new and exotic equations for orbital mechanics, and it's as follows. 1. Start with Newton's awesome equation. And Newton's awesome equation, which if you guys have been following along, you should know it by heart right now. The double time derivative of your position or your acceleration is equal to the negative of your gravitational parameter over the radius of the magnitude of your position vector cubed multiplied by your position vector. All right, that defines what two-body physics is, what two-body motion is. That's the equation of motion for two-body motion. Okay. Hey, oh, it's an auto host. Thanks for the auto host, man. Okay, so 2, right? Perform. So 2 is perform nonsensical arithmetic. Perform some nonsensical arithmetic to the equation. Nonsensible. There, nonsensical. What is that? Nonsensible arithmetic. So we're going to do things to both sides that don't make any physical sense at all, but we're going to do things to both sides. And then 3, manipulate. And we're going to arrive at other awesome equations. I need tea. So that's kind of been the way we've been approaching these problems, right? We start with Newton's awesome equation of gravitation. We perform some weird arithmetic move that doesn't have any physical meaning to it. We're going to manipulate it, and we're going to arrive at something that's even cooler. This is what we have done for the orbit equation. That's what we did for the orbit equation last time. For both parts of the orbit equation. And that's what we're going to do this time with the Vis Viva equation. We're going to do the same exact thing, okay? So again, last time you allowed me 3 nonsensical arithmetic moves. This time you're only going to allow me 1. I'm going to make 1 arithmetic move that just doesn't seem to make any sense. And yes, now when I undo, you don't see that nasty thing up here right in the top of the screen. I finally found out how to get rid of that. Took me long enough. Let me drink a little bit more of my tea here so I can wake up for you guys. Alright, the music is distracting. I'm taking my headphones out for a little bit, but I can't hear you. I can see what you guys are saying. So go ahead again. If you guys have any questions in chat, then let me know. Actually, do you guys want yeah, I don't know why I keep saying that. Nonsensible. There's a better word for it because it is sensible. Obviously, it's sensible because it helps with arriving at the equation that you want. So it's sensible. Maybe perform arithmetic with no physical meaning is a better way to put it. Because they're sensible, right? We have to do them to derive the equations, but they just don't have a lot of physical meaning to them. So I think that's the better way of saying that. All right, so let's move onward then. So we've done this again with the orbit equation. We took Newton's law of gravitation, we did some work on it, and we derived something else. We're going to do the same thing with the Vis Viva equation today. And as we know, the Vis Viva equation is the specific energy of any orbit is equal to velocity magnitude squared over 2 subtracted by your gravitational parameter over your position vector. Again, if you guys have been following along so far in this class, you should know this equation by heart now because of how many times we use it. If not, then it's not a problem, right? Just go back and look at the notes, okay? Just go back and look at the notes and you'll be able to, good to know, Oyoshiro, good to know. But just go back and look at the notes. All of the derivations that I've already gone over are there, and you'll be able to see that content. So E is equal to V squared over 2 minus mu over R. This is known as the Vis Viva equation. Vis Viva equation. The other word, or the other phrase that we provide for this equation is the living force equation. The living force equation. Okay, that's the other way that we describe this. And again, Newton's gravitational law, Newton's two-body gravitational law is this: the acceleration felt by any body upon another body acting gravitationally on it is equal to the gravitational parameter of the first body over the magnitude of the position vector with respect to that first body cubed multiplied by the position vector. Okay, so that's Newton's gravitational law. We are going to take this and we're going to try to get to here. That's the goal, okay? So, without further ado, nonsensical move 1. No, I said it again, didn't I? Nonsensible move 1. Take dot product of both sides with R. So we're going to take dot product with our position vector. That's what we're going to do. And again, if you guys are just coming here for the first time, if you are a little bit confused as to what's happening, just go over to the notes and you'll be able to follow along. Don't worry, it's really not too difficult, the stuff that I'm going over right here. So we're going to take that equation, we're going to multiply with the dot product by both sides with the position vector, right? So now we have the acceleration vector. Oh crap, it's r dot. Excuse me guys. My nonsensible move there was nonsensible. Now, what I really want though is r dot. I'm multiplying each side by r dot. And remember, for those of you guys that are just joining, maybe I should write down these assumptions again, okay? And even for me too, because we could probably use a refresher, right? So r is obviously equal to r. What else do we know? We know r dot is equal to velocity. That's what this notation means. We know that r double dot is equal to acceleration, the derivative of velocity, so on. Velocity in this case is the time derivative of r. And acceleration is the time derivative of velocity. Okay. What else do we know? We know if we take the dot product of two vectors, the response is just r squared. We also know if we take the dot product of the vector and the time derivative of that vector, the response is just the scalar multiplication of the magnitude of the vector and the magnitude of the time derivative of that vector. So these are a few assumptions that we can make through this derivation. So we've got r double dot, the dot product of acceleration with velocity, right? Because we're just taking this equation and we're taking the dot product of both sides with r dot, mu over r cubed, r dotted with velocity. Okay? Here's the thing. I mentioned this last time, right? What we want, as you can see here, you see dots in this equation. You see dots in this equation, right? But we don't see any dots in this equation right here, right? We don't see any dots in Vis Viva. So we need to put everything on a level playing field, right? Whatever level of time derivatives that you're at, we need all terms to match up with that. So if you've got a double derivative of one thing and then you only have a single derivative of another thing, well, that's not good. You need to line up all of your derivatives. Right now, all of the derivatives in the Vis Viva equation line up, right? There's no time derivatives. In this equation, in Newton's law of gravitation, there are time derivatives. That's no bueno. So what we want to do is we want to try to manipulate this equation in some sort of way so we're on a level playing field. So I'm going to write that as a note. For derivatives we want, and in quotes, a level playing field. That's the goal here, a level playing field. Okay, so let's do some work here, and the way we're going to separate this work out is this. This side of the equation is going to be denoted as LH for left-hand side. Okay, and it's going to be in this bluish color, blue, purple, whatever it is. Not the best with colors sometimes. And this side of the equation is going to be the right-hand side of the equation. And I'm going to keep everything color-coded for you guys so it's a little bit simpler to follow along. Okay, so let's start with the left-hand side of the equation. Again, it doesn't matter what we do to manipulate this equation as long as at the end of the manipulation, the time derivatives are all on a level playing field at the end. Okay, that's the goal here. That's the goal. So, first thing to note, let's take a look. We're going to start with the left-hand side, okay? So let's start with left-hand side, LH side, left-hand side of the equation. We're going to do some manipulation on the left-hand side of the equation, which is acceleration dot product with velocity. Okay, we're going to see what we can do. And we're going to take a look at something, right? We know that dot product rule, it's technically not what it's called. I forget what it's called, actually. Well, I'll just call it a derivative theorem. It's not the best way to put it, but theorem is this, right? If you have d over dt of a and b, okay? If we want to take the derivative of this, all we have to do is this. It's equal to a multiplied, or with the dot product, it depends if it's a vector, times d over dt of b plus b d over dt of a. Right? So this is what, hey Mank, what's up? So this is what the, I think it's called the dot product rule, but I forget exactly what it's called. This is a derivative theorem, right? If you're multiplying two things inside of a derivative, this is how you separate out the derivative, okay? So, we've taken note of that, so let's go like this then. Okay, cool. So, let's zoom down. We're going to note something kind of fancy that you can do, right? So, note this. Weekends are always too short, man. Note the following. Check this out. This is pretty cool. If we take a look at this, the time derivative of velocity dot product with velocity, okay? Let's take a look at this. Now, again, to do this, we need 1 derivative of 2 plus 2 derivative of 1. Okay, so it's going to look like this. 1 derivative of r dot plus r dot derivative of r dot. Okay, that's what it is. You arrive at this then. You have r dot product with r double dot, or position dot product with velocity, plus position, velocity dot product with acceleration. Okay, which is equal to 2 r, or velocity dot product with acceleration, and that's equal to the derivative with respect to time of r dot r dot. Okay, that's what that's equal to right there. It's just 2 r dot product with r dot. Okay, that's what it is. Now, if you notice, we have r dot r double dot. Looks pretty similar, right? It's off by a factor of 2 though. So if we just divide by 2, then we've got a solution for this that puts everything on a equal playing field, right? So check this out then. We then know that r acceleration dot product with velocity is just equal to 1/2 derivative with respect to time of r dot dot product with r dot. Okay, and we also know this. Let's take a look at this theorem that we just wrote down here, right? We know that a vector dot product with itself is just the magnitude squared, right? So then we can go like this. This is equal then to 1/2 d over dt of, again, it's just velocity dot product with velocity. It's just different notation. Is equal to 1/2 d over dt v squared, and since this is a derivative, I can pull that into the derivative, d dt, v squared over 2. Spoiler alert, guys, v squared over 2, right? So then we have determined that this right here is exactly equal to the left-hand side of this equation. They are exactly equal to each other. Absolutely exactly equal to each other. This right here is equal to left-hand side. All right, that's what we just proved. Hint. Might come into play somewhere, just saying. But let's keep an eye. Let's keep an eye on that equation. All right, now let's move on to the right-hand side of the equation. Right-hand side. So we've got an equation for the right-hand side that puts everything on a level playing field. We're going to do the same thing with the left-hand side now. Okay, so sorry, I may have just said that backwards. I apologize. I haven't had my tea yet. Right-hand side of the equation. Let's take a look at the right-hand side of the equation. Okay. Now the right-hand side is, so I'm going to copy it back down so we have it. It's this sucker right here. Negative mu over r cubed multiplied by the dot product of position and velocity. So we've got negative mu over r cubed multiplied by the dot product of position and velocity. Okay, this is the left-hand side of the equation. And again, we know a few things, right? We know that's horrible. Sorry, that was the worst end. We know two vectors. So a vector, the dot product with the time derivative of that vector is just equal to magnitude of the vector and the magnitude of the time derivative. We also know, right, if we want to take the time derivative of 1 over r, what would that equate to? For anybody that has gone through calculus, try to answer this question, right? What would this equate to? If you're taking the derivative of r with respect to time, just like this, what would be the response? So the response would be this. The response would be the time derivative of 1 over r is then equal to this term, right? You're just going to subtract another power by it, right? Nope, we're not integrating, Mike. We're not integrating. We are not integrating. Yep, you got it. So what it would be is negative 1 over r squared multiplied by dr dt. Okay, that's the derivative. That's the derivative right there. Okay. Negative 1 over r squared dr dt. Okay. Now, and again, we also know that r with the dot product of r dot is just r dot. So really, we know this. We know negative. Yeah, that. Oh, you got it right, Meg. Negative mu over r cubed. Dot product of the position vector and the velocity vector is really just equal to negative mu over r cubed r dot. Okay, well, guess what? We can simplify a little bit further, right? We have negative mu over r squared r dot. Well, check this out, okay? This looks a little bit similar to the derivative of 1 over r, right? In the sense, right, remember, r dot, that notation is just dr over dt. That's all that notation is, right? So then we've got this, negative mu over r cubed multiplied by the dot product of position and velocity, which is our right-hand side of that equation, is equal to, right, negative mu over r squared, negative mu over r squared, whoa, don't know what that was, r squared, dr over dt, and that's just equal to, check this out, well, hold on a second, there was a question, I think. From the equation to the result? Yeah, sure. Yeah, we can do it that way. I don't know why you would want to, but yeah, you can absolutely do it that way. So you start with the equation, and then... So you're saying you start with Vis Viva and try to derive Newton's law of gravitation? Sure, there's absolutely ways to do that. It's typically easier to start with Newton's law of gravitation and then go to Vis Viva, because Newton's law of gravitation is a little bit more fundamentally, I don't want to say robust, but right, Newton's law of gravitation is a physical thing that we observe in the universe, whereas the Vis Viva equation is just a characteristic of some geometric shape. Well, it's not geometric, right? It's just a characteristic of an orbit. So it's typically, again, like you start with the fundamental, and then you can derive all things from there. But yeah, I guess if you start with something like the Vis Viva, then yeah, you can go back to Newton's law of gravitation. I don't see why you wouldn't be able to. There's absolutely ways to do that. It's just taking the work and doing everything backwards. So anyway, guys, again, we're trying to put everything on an equal playing field here. And check this out. This right here, let's take a look. This right here is just this multiplied by mu, right? So really, that's just equal to mu, and then this right here, d over dt of 1 over r. And guess what? Mu is a constant, so we can go like this, d over dt of mu over r. Okay? And again, this is exactly equal to the left-hand side of the equation. Or the right hand, excuse me. Right hand. This is exactly equal to the right-hand side of the equation. Okay? And we have something that's also exactly equal to the left-hand side of the equation. And guess what? They're at the same exact level. The same exact level. So we have this now. The left-hand side of the equation, d over dt of v squared over 2 is equal to, and I want the colors to be perfect here, is equal to, and now let's look at the right-hand side of the equation that we derived. Again, left hand and right hand. D over dt of mu over r. How awesome is that? Everything is on an equal playing field now. And what we can do is move everything over to one side. Whoa, that was not so good. Okay, so let's move everything over to one side now, right? So d over dt of v squared over 2 minus mu over r is equal to 0, right? Because we just subtracted this over to this side. And let's integrate, right? Let's integrate over time. And if we integrate, we get what's called a constant of integration. So let's do that, right? V squared over 2 minus mu over r is equal to some constant of integration, right? And again, this is called a constant of integration. So it's a constant. Oh, integration. It's a constant of integration. The constant of integration is constant. And we give this constant a specific symbol, and we use this constant relatively often in orbital mechanics. And we call this constant, we call this constant script E, which is specific energy. Okay, specific energy has the following units. Wow, nice Y. Specific energy has the following units. It has units of length, so it would be, for example, kilometer squared per time squared. Okay, those are the units. I really should do a units class one of these times to make sure we're up to date with all the units and all the different units and everything of this. But all right, so now we've got a constant, right? A constant of integration, and we call this E, which is short for specific energy. Which brings us to, oh, okay, I don't want a highlighter. Which brings us to our following equation. Specific energy of any orbit is equal to v squared over 2, the velocity squared over 2, minus mu over r. Okay? That was pretty sloppy. Excuse me. Okay, E is equal to v squared over 2 minus mu over r. Okay? Let's highlight this in. It's important. It's really important. We use it all the time. V squared over 2 minus mu over r. And what do we call this equation again? We call it the Vis Viva equation. Vis Viva equation. Vis Viva equation. That's what we call it. Vis Viva. Hey, Kelly. What's up? Kelly, we just derived Vis Viva equation, and it was pretty awesome, man. So again, let's go over what we did here. Oh, it was a question, Kelly. It was a question, but I answered the question myself. So. Okay, so let's go over what we did here. All right. Now again, there are a few steps here. There's definitely quite a few steps, but let's just go over it. Take our time. And if you guys have any questions at all, just ask. All right, just ask. So here is how we approach orbital mechanics. How to derive orbital mechanic equations. Here are the steps for how to derive orbital mechanic equations. Okay, you start with Newton's awesome law of gravitation. The acceleration is equal to negative mu over r cubed multiplied by the position vector. We perform some step of arithmetic that has absolutely no physical meaning and it seems completely nonsensical. That's the second step. And then the third step is that we manipulate that equation and we arrive at some other awesome equation. That is what we do for orbital mechanics. We start with Newton's law of gravitation. We perform some arithmetic on it that might not make a lot of physical sense at first, but then we manipulate it until it makes physical sense and we arrive at another awesome useful equation. That's what we do. So here was the goal here. Here was the goal. We wanted to get to this. Your specific energy, the energy of your orbit, is equal to v squared over 2 minus mu over r. And we wanted to get there from here, right? We wanted to get there from here, starting with Newton's law of gravitation. Start here. Start here. You always start here. Start here at Newton's law of gravitation. And I said this. I said, allow me one nonsensible move that doesn't make any physical sense. I said, nonsensible move number one, allow me to take the dot product of velocity to both sides of the equation. It doesn't make any sense and it doesn't have to make sense. But that's what I did. I took this equation and I took the dot velocity of I took the dot product with velocity to both sides here. And what I said is you can take a look at Vis Viva, and Vis Viva has no derivatives in it. It doesn't have any time derivatives in it. Excuse me. But there are time derivatives in this equation right here. We've got r double dot. We've got a double acceleration, a double time derivative. What we wanted to do was throw everything on what you can consider to be a level playing field, where all of the derivatives are at the same level. They're either all first derivatives, they're either all zero derivative, they're either all third derivatives. It doesn't matter. We wanted everything on the level playing field. So we're going to use this theorem of derivatives for multiplication, where if the derivative of a dot b is equal to a dot dt or d over dt of b plus b d over dt of a. Okay, so we had this, right? We noted this, that d over dt of just r dot it'll get weird, ends up being exactly equal to half of the left-hand side of the equation. So what we ended up doing was just we substituted the left-hand side of the equation for half of this value. And we determined also that the dot product of two vectors is just the magnitude squared. So we arrived at this. The left-hand side of the equation is just equal to v squared over 2. And then we looked at the right-hand side of the equation, and we had this. And we used another one of our vector theorems, that r dot product with the time derivative of r is just their magnitudes multiplied. And then we took a look at this. D over dt of 1 over r is negative 1 over r squared dr over dt. And then we noticed how the right-hand side of the equation note the following. What do you mean? Where did I write note the following? Note the following. Note the following. Oh, right here? So my previous question was about is it ready to go away the other direction from the equation of the result. So are you saying is there any way to go from this to here? Well, I mean, you're not doing anything in this step. I mean, this is just well, it's just a theorem. I can't tell you how they derived this vector theorem, but it's just a theorem for vector derivatives, and it's a theorem for any derivative. So yeah, I mean, if you have this, then you can move to here, but if you have this, then you move to here. R dot dot R dot comes from nowhere. R dot dot R dot comes from nowhere. Yeah, you're right. It does come from nowhere, and the reason it comes from nowhere is because of the fact that we notice that this is similar. Okay. Well, yeah. Well, here's the thing. Oyashiro. That's part of mathematics. Part of mathematics is determining, right? Is determining something like this, and you look at it. And if you know enough of your mathematics, then you know that there's a similarity into this derivative theorem. So it's pattern recognition sometimes, Oyashirox. But yeah, I mean, you can go backwards. But part of that is just kind of knowing Oyashirox. You're right. It didn't necessarily come from nowhere, though. It came from the fact that this is exactly equal to half of that. It didn't necessarily come from nowhere, but that's an absolute truth. It's an absolute truth about this derivative theory. Instinct or intuition. Intuition is a way I'd like to think about it. Intuition. It's just from doing it over and over again, you can recognize that the double time derivative of a vector with the dot product of the time derivative is actually just equal to half of the time derivative dotted with itself. And again, like I showed why that was true here, but yeah, but now that you know this, right, the next time you see this pattern, then you can use it again. And that's kind of what math is. Once you recognize a pattern, then you can use it to manipulate other equations. That's exactly what it is. But all right, so now we've got the left-hand side on all equal playing fields, right? This is all at the same level of derivative. And then we have the right-hand side right here, right, which is a little bit more complex at first, but then we notice this. Oyashirox, I hope that answers your question a little bit. Yeah, sometimes it's just pattern recognition. That's what we did there, Oyashirox, is no different from deriving anything else. It's no different from anything else that we derived. It just looks a little bit different because you probably haven't seen it before. So we know that R dot product with R dot is just equal to the magnitudes, right? We went over that. We've already mentioned that as one of the assumptions. And then we took a look at this, right? And we see d over dt of 1 over r is actually equal to negative 1 over r squared dr over dt. And this is the same exact thing, Oyashirox. Once you simplify the right-hand side down to here, it's just a matter of pattern recognition. It's a matter of noticing that this has a strange resemblance to d over dt of 1 over r, all right? Such that what it's really equal to is just the negative multiplied by a negative of d over dt of 1 over r, and then you just slap a mu on the front of it. You just slap another constant on the front of it, but they're exactly equal to each other, and that's just, again, it's just a mathematical manipulation that we can do in calculus. It's just one of those things that we can do. And no, I'm not going to go over the derivative for why that's true, because that's like 400 level of mathematics, and honestly, it would take hours. If you want to know more about derivatives, then I highly recommend. Oh no! Don't be sorry about that. Yeah. No, Oyashiro, I always tell you guys, ask why, right? Ask questions. Ask me why I'm doing any of this. It keeps me on my toes too. I like it. But yeah, it didn't necessarily come out of nowhere, right? We just noticed that this happened to be equal to this. Right? So we could swap the two out in the equation. And that's exactly what we're doing here. So we notice that the right-hand side of the equation, after all this derivation, ended up being equal to this. What's a derivative? I noticed a kappa, so I'm not going to answer that question. If there wasn't a kappa, I probably would have answered that question for you, Tender. What's going on, Tender? How are you? But if you don't know what a derivative is, if you guys really don't know what a derivative is, then Simple definition of derivative, right? At any given time, this pen has a position, right? Its pen has a position to it on your screen, which would be the position. But also at any given time, the pen is moving in a direction, and moving in a direction is the change in your position. So that's the derivative of position, and you can keep going down that rabbit hole for as many derivatives as you want. If you want a better explanation of derivatives, then I'd highly recommend, oh, more tea, cool. then I highly recommend going online, looking at some calculus notes. So anyway, now we have the left-hand side of the equation and the right-hand side that are exactly equal to each other. T time, yeah, you bet, Oyashirax, T time. And we got the left-hand side and the right-hand side that are exactly equal to each other, and they're at the same level of the playing field, right? Tender, that's the thing, man. I'll always answer questions like that. They're on the same level, right? Same level of the playing field. So now check this out. We can move this over here, and we can throw everything in the same derivative, and it's equal to 0. And once we integrate, we get what's called a constant of integration, all right? So we have a constant of integration here, and we call this constant specific energy. This constant has units of kilometers squared per second squared. That's a bad habit. Square kilometers per square second is really a better way to say that, right? Because if you say this, hold up, let me check my phone, making sure I'm not missing anything. Okay, never mind. We are good. Okay, so anyway, oh wait. What was that? Excuse me. Sorry, 1 second, guys. But that's important. You need to notice the subtlety there between saying square kilometers and kilometers squared. They're different from each other. They're different, right? So if you say 8 meters squared, right? That could either mean, you need to have the units correct. Yes, you do. But look, 8 meters squared, if you say that, that can either mean 8 meters squared, or it can mean 8 meters squared, which are two completely different things, right? But if you say 8 square meters, then there's no ambiguity. That means it always equals 8 meters with a superscript 2 after the meter sign. So this is 8 square meters. 8 meters squared could mean two different things, two entirely different things. So just be cautious about that when you're saying, like, obviously here I'm saying velocity squared, but if I'm using units, velocity squared is in units of square kilometers per square seconds. That's the proper way to say that. And it would be cubic kilometers per cubic seconds if you were going up to cube. But you need to make sure that this ambiguity is get it out of your head, okay? I hear it too often, and I do it too often. I'm trying to fix it. So that's what you should work on this week, trying to fix that ambiguity. All right, guys, I'm going to ask you a couple of questions in rapid succession. You guys are going to try to answer them. For every no, I'm not going to do that. Never mind. I was going to say that for every question you get right, you're going to get space coins, but guys, the currency doesn't get you anything. It's a neat little thing to do mini games, and I'm probably going to do away with it for a while. After a little bit, sure. More tea. I need more caffeine. I'm probably going to get away with it. Don't worry about the currency or anything, but let's see who can answer this first. If I increase velocity, what happens to energy? And I'm going to make a graph for this. So let's use Vis Viva now, right? E is equal to V squared over 2 minus mu over r. What happens when I increase velocity? So let's go like this. Squares? What squares? Were you talking about this ambiguity up here? MetaReal, I think I missed your follow, man. Welcome aboard. Thank you, Lord Gainoff. You're absolutely correct. If we increase velocity... Oh, come on. So let's take a look, right? So we're going to go like this. So we're going to go adjustment column. Result. Okay? So if we increase the velocity at any given point of your orbit. So if we see velocity goes up, then specific energy goes up. Okay, let's do this for the other ones, all right? What happens when we increase the gravitational parameter of the body? What happens when we increase the total mass of the first body? What happens to orbital energy? So mu, let's say mu goes up. What happens to total orbital energy? Yep, total orbital energy goes down. You got it. All right, and what happens, lastly, when we increase position? So let's say that we move further out. What happens? If we move further out from our orbit, what happens to our orbital energy? This one's a little bit trickier. But if we increase position, what happens to orbital energy? You're right. It increases because we're subtracting from a less larger number. That's what's happening. So energy also increases. Okay? Let's go over some example problems using the Vis Viva real quick. And this is not the worksheet quite yet. Okay? I don't need that. Energy also goes up. Okay? Let's say this. So again, let's say that we have this. Again, I'll write down the Vis Viva equation one more time for you. V squared over 2 minus mu over r. Actually, you know what? I'm not going to do this quite yet because it doesn't make a lot of physical sense. So we're not going to do that. Oh, actually, that would be kind of fun. Yeah, okay, so I've got a question for you guys, right? So every orbit, and again, v squared over 2 minus mu over r, right? So, and I've gone over this before in a previous note, but I really should re-derive it here. So, yep, you can use this. Energy is constant for any orbit, right? Energy is constant. And there's a few things that we notice from this equation, right? So let's say that this is required. No, you can think of it as any way you want. The reason I had broken it down to meters squared per second squared is that joules is not part of the standard SI base system, right? The base system you need length, you need time, and you need mass. And I think you need a few other things, but length, it would be meters, time would be seconds, and mass would be kilograms, right? But joules, right, which is a force multiplied by distance, kilograms times meters per second squared multiplied by meters. This is a joule, and then you divide that by mass, right? Joules per kilogram. You divide that by kilogram, cross off the kilograms, you get meters squared per second squared. The reason I like doing it this way, meters squared per second squared, is just because it's in the base system. But yeah, you can think of joules per kilogram. Yeah, that's a totally fine way of thinking about it. There's nothing wrong with that at all. I just like keeping everything in the base units. Which, you know, if it makes more physical sense for you to think about it as joules per kilogram, then, you know, think about it as joules per kilogram. That's totally fine. But anyway, guys, let's take a look at something, right? Again, orbital energy is constant, right? Which means that if I increase velocity, what happens to position vector? In order for this to be constant, right? If this parameter goes up, then this parameter would have to go down, right? Because we need this to be constant. And we know that our gravitational parameter of every body is constant. So if velocity goes up and if this goes down, the only way for this value to go down, right, or to go more negative, is to decrease radius, which increases this value, which makes you subtract by a larger amount. So basically, for same orbit, when velocity goes up, position goes down. And when velocity goes down, position is up. All right. We notice these terms as apoapsis and periapsis of an orbit, where at your periapsis, your position vector is the smallest and your velocity is the highest, and then at your apoapsis, your velocity is the lowest and your position vector is the highest. Okay? So we've got v squared over 2 minus mu over r. We have derived the Vis Viva equation. We've derived it up here. And then we saw exactly what changes, right? If we adjust velocity, then energy increases. If we increase the total mass of the body, then energy decreases. If we increase how far out we are in the orbit, then energy also increases, okay? So we now have a few relationships by just tuning, again, these are just by tuning one parameter at a time. Single parameter tuning. Okay, these are just single tuning parameters. And we see what happens to orbits when we change things like velocity and position over time. So this is how you manipulate and use the Vis Viva. I released a worksheet, and for those of you guys that don't know or have not seen the worksheet yet, there is a command for it, okay? All the class materials on there, everything that I've covered so far is on there, okay? Every single thing that I've done is on there. Including some extras that I've went over, including worksheets, including all of the notes that I go over. Everything is on that website, okay? How did you set that up for a spreadsheet? That's like a Lambert optimization problem. How did you do that without scripting? My orbital transfer and intercept. Yeah. I'm curious to know how you did that without solving for Lambert's. Lambert's equation is another thing that I'm going to be going over a little bit later in this class, where it's a little bit more complex. Anyway, without further ado, we're going to go over the answers to the worksheet now, okay? So, if you haven't done the worksheet, well, don't feel pressured to leave. You can obviously take a look, but if you don't want to be spoiled, then, that's also fine. It's all up to you, right? But I'm not saying that you have to leave if you haven't seen the worksheet yet. There's nothing wrong with that. I'm going to upload these notes for you guys again on Vis Viva and how to derive it. I'm going to go get some more tea real quick, so hold on a second. All right. So I guess it's just an approximation then, Lord Genoff. All right, so here's what we're going to do. We're going to go over the worksheet now. So let's see. Deriving Vis Viva. This is an extra, right? Mod book. Wait. This is not KOS notes. This should be in AERO 101. And this is E. Do you know how far you want to go with this class? I want to take it into different heights. From eccentricity to delta V. What I want is, for example, guys, I'm going to start going into orbital mechanics history. Like all of the different transfers and maneuvers that all of the Apollo missions made. I'll be going over the flight profile of the Mercury and the Gemini missions to see what they were doing earlier on in rocketry and see how their trajectories changed over time. I'll go over lunar rendezvous and docking concepts as well. I plan on going over some history stuff as well. I plan on expanding not necessarily just into more mathematics. I plan on expanding into different things as well. I know it's been heavy on the math, but we really needed to focus on these orbital equations. We needed to get these orbital equations out of the way. And now we've got most of them out of the way, so we can start doing cool things too. This was extra over E002. Altitude of geo orbit. Okay. I hope so, Oyashirox. I hope it will. Do you prefer Oyashiro X or Oyashirox? I don't know how you want me to pronounce your name. Sorry about that. So anyway, we've got lesson 4 now, Deriving Vis Viva. We've got 2 extras. We've gone through a lot of other things too. So anyway, we're going to go over worksheet number 1 now. And I think there is a way to import a PDF, right? For those of you guys that have used OneNote before, I'm pretty sure there's a way to import a PDF, right? Let's try it out. AERO 101. There we go. Worksheets. Insert printout. Oh, well that worked out perfectly. Okay. Just drag it? Yeah, that's what I did. I don't know if I wanted to insert the printout though. I really don't know what I wanted to do there. Let me go like this. Let me try it one more time. And let me try it the other way. Oh, that's just attaching the file. Never mind, so I do want to insert the printout. Got it. Okay. We are go to look over this stuff. Okay, let's start right here. Oh, quality-wise that looks iffy, but that's okay. Should give you an option to not have printout. Well, there was no option there, unfortunately. Okay, let's go back into full screen mode so we can take a look at this. Let me just make sure it's all nice and centered. Okay, so first off, and guys, I don't know how I want to do this. I think every once in a while I'll ask you guys questions and you guys can go ahead and shout out the answers. If you guys know the answers to any of these, feel free to shout them out. But we're going to start in the beginning, right? So which famous philosopher said this? And yes, we started with philosophy in this class. Philosophy used to be physics before physics and science were its own category. So who said this? We inherently know all ideal forms of all objects, and our senses simply allow us to see recollections of these objects. So what this philosopher said is basically, we already know all of the ideal forms, and we're just when we see an object in person, right? How can I know that that's my cell phone? How do I know that it's my cell phone? Well, I'm just born with an idea of what the cell phone is, and I simply recollect what the cell phone is. Now, obviously, we don't know that's right anymore. But I think I'll leave the philosophers for you guys to guess, right? And I'll write out some other things. So we know the AERO is the International... Oh, jeez, that's way too thick. Oh, come on. Why does that keep happening? What if we just move them all over? Like that. Yeah, sorry about that, guys. So we know the AERO. There we go. That's pretty good. The AERO is... this is a better size. The International Earth Rotation Service. Okay, and we have another philosopher that said something else, and this philosopher said God is perfect and created perfect circular orbits, and that the Earth is the center of everything. So I'll let you guys, again, I'll give you guys some time if you guys had came to the other classes to try to guess for that. But anyway, argument of periapsis, we denote that as a small omega, right? This is omega right here. And we have somebody else. They used Tycho Brahe's observations to derive an orbital mechanics model consisting of 3 independent geometric laws. Okay, who came up with an orbital mechanics model that had 3 laws in it for orbital mechanics? So the GCRS is the geocentric celestial reference system. And this is a common Cartesian coordinate system, right? Cartesian meaning X, Y, and Z. It's a common Cartesian frame that we use here centered on the Earth to make sure spacecraft are in a given position at any given time. And again, I'm gonna come back and do all of the guys first, all of the philosophers and mathematicians afterwards, to give you guys some time to guess. But who was the author of Principia Mathematica Philosopha Naturalis? And hopefully you guys can at least get this one. Who was the author of Principia? And then we have right ascension right here. So this large omega is known as RAN, right ascension of the ascending ASCENDING node, or RAN. Try not to say RAN, guys. Right ascension is the proper way to say it. It's a bad habit for me to say RAN. Don't use RAN, use right ascension. It's a bit more proper. So, author of Principia was Newton. Oh, Yoshirox, you got it, man. It was Newton. Okay, STEM, we already know STEM, right? We better know STEM. Science, technology, engineering, and math. That's what STEM is. Who said this? Plato was wrong. We develop these ideal forms over time. And again, this is something else, right? I'll go back and I'll do all of these. I'm not requiring you to guess it, obviously. I'm just letting these stick with you a little bit. But he basically looked at Plato's work and he said Plato was wrong. And he said we look at ideal forms in our mind over time. And we use our senses to... Plato. The first quote is from Plato. Yeah, you got it. First quote is absolutely from Plato. So let's go back and let's fill that one in. The first quote is from Plato. Plato said that we inherently know all of these ideal godly forms, but forms meaning anything, objects or mathematical models, it doesn't matter. But our senses are just recollections of them over time, right? Saint Agostino? Not quite, Mr. CAB. Not quite. Mr. Cab, got it now. The second one is not quite, it's not quite St. Agostino. I think it was around the same time, but not quite. So there's, anyway, so Plato was wrong. We develop these ideal forms over time, using our senses. We also have ITRF, the International Celestial, not celestial, this is terrestrial, this is different now. International Terrestrial Reference Frame. You got it. You got it. That's not what it is in English, but you absolutely got it. Good job, Mr. Cap. It's Ptolemy. It was Ptolemy. It was Ptolemy. You got it. It was Ptolemy. So we've got, and gravitational parameter we define as this mu character, right? That's what we define as gravitational parameter. We've got a few more to fill out, though. It looks like we have two philosophers that we haven't filled out yet, or philosophers or mathematicians. We've got one. He used Tycho Brahe's observations to derive an orbital mechanics model consisting of 3 different philosophers. And then we have another one down here who looked at Plato's work and said that Plato was wrong, and he said that we develop these ideal forms over time instead, using our senses. So the answer to these two are as follows. It was Kepler. Kepler is the astronomer and the mathematician that used all of Tycho Brahe's observations and derived an orbital mechanics model that consisted of 3 of Kepler's laws, the 3 Kepler's laws. One was Tycho. Was the Tycho one Kepler? Yes, condition of man. You got it. The Tycho one was Kepler. It was Kepler's law. Kepler was the one that used all of Tycho's observations to get to the 3 independent geometric laws. You absolutely got it. And then the other one down here, it was Aristotle. Aristotle was Plato's student, and Aristotle said Plato was wrong, and Aristotle says we use our sensors instead. Okay, we use our sensors. I'm not a robot, I'm telling you. We use our senses. All right, we use our senses to develop these ideal forms over time. Instead, it's a little bit different. So we've got our table filled out here. Okay, we've got our table filled out. Next section, postulates and laws, right? We've got 3 of Newton's laws, and we've got 3 of Kepler's laws. Let's try to fill these in. Let's go like this. No, I'm not a robot. I'm not a robot, I'm telling you. Let's go like 1, 2, and 3. If you guys know any of Newton's 3 laws or any of Kepler's 3 laws, just go ahead and shout them out. And I'll give you guys a little bit of time, right? I'll give you guys a little bit of time to guess if you know any of these 3 laws. Okay? I'll give you time. I won't give you too much time, but I'll give you some time. No, I'm not a robot. Alright, so I'm going to start filling these in. And I'm going to go in logical order here. Whoa, I didn't want that. Well, that's not good if you don't know how to express it in English. Since I learned this stuff, I know, Tender. A body in motion remains in motion until acted upon. Yes. You got it. And a body in rest also remains in rest until it's acted upon. And condition of man, to throw those 2 things together, you can also say, just in general, the inertial state of an object is constant with a 0 net force. Okay? This is a way to combine both. An object in motion is equal in motion, and an object at rest stays at rest. This is a way to combine both of those into one statement. Everything has an equal opposite reaction. Tender Vittles, you got it. Condition of man, you also got it. That's the 3rd law. For every action, there is an equal and opposite reaction that follows. There's an equal and opposite reaction that follows. Reaction. Yep. Okay, I think these are the only 2 that you guys have filled out so far. But that's good. That's good. You guys knew some of these. So moving on. So we've got Newton's 3 laws. The inertial state of an object is constant with 0 net force. And then for every action, equal and opposite reaction. The 2nd law defines what happens when we do have a net force on the body. Okay? I can't remember the missing one. It's the following. The following, Newton's 2nd law is net force on the body, on a body, is equal to change in momentum, right? Momentum, okay? And he calls this net force. He introduces this word force, and force then is a vector, is equal to the change over time of your momentum, which is just mass multiplied by velocity. Okay? In other words, right? In other terms that you may have seen this equation before, you may have seen this equation looking like this: F is equal to ma. It's probably another format that you've seen this equation. But that's the other one. The net force that you see on the body, it's equal to the change in momentum over time. That's what that other force is. Alright, so we've got Newton's 3 laws. So it doesn't look like anybody has shouted out Kepler's 3 laws. So I'll go over Kepler's 3 laws. And Kepler's 3 laws are as follows. The first law is that all planets, and again, these are all things that he derived before we even had before we even had calculus. He derived all of these before we even had calculus. It's crazy, okay? The Apple explanation, that's Newton, and that's Newton's gravitational law. Newton's gravitational law, well, I think it was part of Principia, but oh no, I don't think it was part of Principia. Principia was just inertial movement, and then he released the law of gravitation later, I think. I'm not too no. Yeah, I think that's how it happened. There's nothing in here, Tender Vittles, that describes gravitation, right? Other than gravitation being a force, right? There's nothing that describes gravity here. This is just Newton. This is just inertial forces on a body, right? You're not limiting yourself here to gravity. But anyway, Kepler's 3 laws are as follows. The first law is all planets, and again, he did this all without calculus. It's crazy, okay? Yep, you knew it, Tender. It was Newton. All planets rotate around the sun. In ellipses. And the sun is at the focal point. It's at focal point. Okay. The second of Kepler's 3 laws is equal to this. Equal area swept in equal time. So this means equal. If you've got an orbit, if you've got a planet, and if you've got an orbit like this, and from delta t time 1 to time 2, delta t1, you sweep out this much space, and then from delta t1 to delta t2, delta t2, you sweep out this much space. If the times are equal, if these times are equal, then the total area under the orbit right here will also be equal. That's his second law. Yeah, that's good enough, Mr. Cab. That's good. So that's the second law, right? Equal area, equal time. That was his second law. And then the third law that he came across, his third law was, oh geez, I'm just slashing up all my work here. The third law that he came across was this, that the square of the period of your orbit is proportional to the cube of your semi-major axis of your orbit. That was his last law. What this really looks like, well, it's a little bit different than this. How did he even find this? Lots of geometry. Lots of geometry, lots of trial and error. It's difficult. It's how impressive is that, Oyashiro? Like, he did all of this without calculus. And again, he did it with several thousands of pages of observations from Tycho Brahe. Tycho had a lot of information about this stuff, so he had a lot available to him to figure all of this out. So anyway, the real equation, for those of you guys that are interested, is p squared is equal to 4 pi squared a cubed over gm. You don't necessarily have to know it, but pi, constant, gravitational constant is a constant, and mass of your body is a constant. So p squared is proportional to a cubed. That was the last. That was the last of his 3 laws that he came up with. So those are our 3 laws. P squared is equal to a proportional to a cubed. Sorry, not equal to. It's not necessarily equal to unless you're in the right units. Okay, keep that in mind. So those are 3 Newton's laws and 3 Kepler's laws. Moving on, let's go over the go, no go. Okay, I'm going to label these just in case while I'm slowly going over to those, if you guys wanted to go ahead, you can shout out like 5 is a no-go or something like that. Go ahead to shout out any of these if you know any of them. 7, 8, and 9, and 10. Okay, so let's start with the first go or no-go, okay? Newton's law of gravitation breaks down on galactic scales and may be only an approximation of the true model of gravitation, right? And we had already determined that 1 is a go. Oh, yeah, sure, so you got it. 1 is a go. We've determined already that Newton's law of gravitation doesn't seem to work appreciably at large scales on the galactic scale. That could be two things, right? One, maybe it does work and there's mass that we don't see, or dark mass, or dark matter. Or, two, the second one, right, is that we just don't know how this equation fully works yet. So yeah, 1 is a go. So let's take a look at 2. You can use Newton's second law in any frame, inertial or non-inertial. And if you go back into the notes, you're able to see that actually, no, you can't use it in non-inertial frames, okay? You can't use it in non-inertial frames. This is a no-go. Newton's second law right here, F equals ma, that's only valid if you're looking at the force in an inertial frame. Okay, so let's look at number 3. The ICRS is not a perfect inertial frame. I don't expect you guys to remember that one because that was just a little tidbit way back in the notes. That's a go. The ICRS is what we consider to we're trying to come up with the most inertial frame that we can reference. And how we do that is we locate very distant quasars in the universe. Thanks, Lord. Appreciate it. We locate very distant quasars in the universe, and we try to come up with an inertial frame using those as sort of waypoints, right? We use them as waypoints. So this is true. It's go. The ICRS is not a perfect inertial frame. We still haven't. There's no such thing as a perfect inertial frame. 4, we do not live in a perfect Cartesian system, and Oyashiro says 4 is a go, and Oyashiro, you are absolutely correct. 4 is a go. We don't live in a perfect Cartesian system. We live on a planet, which means our space-time is slightly warped. If you were to go into orbit, and if you were to move out of the gravity well of the Earth, your space-time continuum would be different. Time in orbit actually passes at a slightly different rate. All of the astronauts on board the ISS right now, time is actually passing at a different rate for them. They're aging at a different rate than we are. Now, this rate is so incredibly small that we don't necessarily see that. But how cool is that? All of the astronauts on board the International Space Station right now are actually in a different space-time continuum than we are. Gravity is affecting their space-time slightly different than our space-time. So they're actually moving at a different rate. Number 5, Copernicus created a heliocentric solar system that completely removed the idea of epicycles from the model. Sorry for the typo. 5 is a no-go. Oyashiro, you got it right. 5 is a no-go, right? No-go. Okay. So, that completely removed. This is the problem. Copernicus still used epicycles in his idea, but all he said was basically, it's a heliocentric model. He did say that part is true, right? It is a heliocentric model, but the problem is, he didn't remove the idea of epicycles. He still had the idea of epicycles in his model. And if you guys want to see these notes and what all these different models are from the different philosophers, then again, go back into the notes. And for those of you guys just joining, just go ahead and go like this, AERO 101. There we go. Go back to the notes and you'll be able to go over all this stuff at any given time. So let's go like this. When Kepler derived his orbital model, we still did not have an equation for gravity. And Mr. Cab says 7 is a go. When Kepler derived his orbital model, we still did not have an equation for gravity. That is a go. As I just said, Kepler was able to derive his orbital model, or his orbit model, without the equation of gravity. He did it all without the equation of gravity. He did all of those by just using geometry. And you can go back and you can actually use Newton's gravitational law to derive those equations, which is really, really cool. It's another proof to make sure that they're absolutely correct. So, number 7, hyperbolic orbits are characterized by negative semi-major axes. 7, Mr. Cab says 7 is a no-go. Isn't it infinite? That is incorrect. 7 is actually a go. Hyperbolic orbits have negative semi-major axes. A semi-major axis of a line, nope, that's not necessarily always true. A semi-major axis of a parabola is infinite, right? So what happens is that you have an eccentric orbit and you keep increasing your semi-major axis all the way out to infinity, and right at infinity is a parabolic orbit. But then once you go hyperbolic, your A wraps all the way around to negative infinity, and your A slowly approaches 0 the more hyperbolic you become. But this is actually a go. Hyperbolic orbits are characterized by negative semi-major axes. The semi-major axis of a parabola is characterized to be infinite. It's a slight difference, but the semi-major axis of a parabola is characterized to be yeah. Okay, so moving on. Yep, you got it, Mr. Cab. So circular elliptical orbits are characterized by positive orbital energies. Okay. I wanted to ask, what is the difference between a parabola and a hyperbola? Well, the difference is this, right? Well, here I can write it out for you real quick. Let's go like this. Let's just add a new page. And we'll go back to that page in a second. So an ellipse, right? An ellipse is just like, well, it's a pretty bad ellipse. It's just like this. And we know a circle is like this. Okay, and these both have very well-defined semi-major axes. The idea behind the parabola is this: the parabola is increasing, in a polynomial sense, right? So as A approaches infinity, your velocity approaches 0. So here's the idea. Exactly at the point of infinity, you're going to slow down, you're going to slow down, you're going to slow down. And remember from Vis Viva, the further R you are, the less velocity you have. And you keep going, you keep slowing down, and then right at the point of infinity, you are exactly not moving anymore. That's what a parabola is. That's what exactly infinity, you are no longer moving. Now, what a hyperbolic orbit is this. A hyperbolic is a bit different. It doesn't approach a polynomial. What a hyperbolic does is it approaches what's called an asymptote. Right? So a hyperbolic, it wasn't the best asymptote in the world. A hyperbolic orbit approaches an asymptote, right? It approaches a line. So it doesn't keep curving down. It approaches an asymptote instead. And there's a lot of hyperbolic math that goes behind defining all of these angles for hyperbolas. And once we go into calculating interplanetary transfers, which is something that I may do in this class, I may not, I don't know. There's things to calculate, like the total delta in between this angle and everything. But the whole idea is that here, and this is actually not A, right? Because that's inaccurate. It's your position. As your position approaches infinity, your velocity shoots to 0. But here, as your position approaches infinity, your velocity approaches a constant, approaches a positive constant value. So here, at infinity, you're still moving away. That's the whole idea. In here, you've just got out of the capture of the orbit. You've just gotten out of it. But then in a hyperbola, you've superseded the object. You're no longer in the object's gravitational, well, you're in its pull, but you're no longer essentially in an elliptical orbit. You're no longer in a returning orbit. You're not going to return, right? At infinity, your velocity is going to have some constant value instead, okay? The math is different, Oyashiro. The math is different. Again, a parabola is a polynomial effect, and a hyperbola is an asymptotic effect. So they're actually a bit different. Parabola, a better way to look at this, Oyashiro, is that parabola you're really not going to see in nature at all, because as you approach velocity at infinity, you're going to have other bodies that are going to pull it forward, and you're going to have perturbations and everything like that. You're not really going to see these. Hyperbolic orbits are a little easier to work with, and they are the orbits that you see for interplanetary transfers. But the math is actually a little bit different, Oyashiro. Just remember, this is polynomial, and this is asymptotic. Okay, that's the difference between them. Okay, so anyway, hopefully that helps. Let's get back to the notes here. And again, guys, just ask any questions you want, all right? That's the whole point. Ask questions whenever you want, and I'll be able to answer those questions for you, hopefully, to the best of my ability. All right, so let's continue on. Circular elliptical orbits are characterized by positive orbital energies. The answer to that question is actually a no. Ooh, that's a little bit too thick. Sorry, let me go fix that. What I wanted was probably this, right? This is actually a no-go. Okay, circular and elliptical orbits are characterized by negative orbital energies. And then, at a parabola, your energy is 0. And then at a hyperbolic orbit, your energy is positive. But your circular and elliptical orbital energies are all going to be negative, actually. You're going to have negative characteristic energy. It doesn't necessarily have a physical significance. It's just a way to tell if an orbit is circular or elliptical. You can think of negative energy as that you have negative energy with respect to that body, right? You haven't escaped the body yet. But once you go hyperbolic and you escape the body, then your energy is positive with respect to that body instead. So, moving on. The derivation for orbital eccentricity is a vector, not a scalar. And the answer for this is a go, right? We've got a go on this one. The derivation for orbital eccentricity, when you see eccentricity, you just think of it as a number, right? Well, that's actually not true. The derivation of eccentricity, and we've gone over the derivation in class, so again, just go over to the notes if you haven't seen them. The derivation is actually a vector. And then to get the eccentricity value we all know and love, you just take the magnitude of that vector. And last thing, calculating, but answer came first. No problem. It's no problem at all, Yoshiro. So calculating rate ascension requires a quadrant check. And let's take a look here. Calculating rate ascension requires a quadrant check. It absolutely does. So this is also a go. We need to make sure that we're in the right component when we're calculating rate ascension for all of our orbital elements. Which, if you want to go over the orbital element class, then we've already covered that again, so we just go over that. So, we've covered all of the entry material here. We're going to go over the problems now. So let's take a look. Alright, so we've got problem number 1 right here. Let's take a look. And there's what I mentioned here is that you can use these as constants in your equations if you have to. I'm not saying you have to, but hint, you have to. So you can use these. You can use these as helpers, right? So problem number 1. Upon starting a new position at a stellar observatory, you just got hired. Congratulations. You're tasked to track and characterize 2 Earth-orbiting objects, object alpha and object omega. So your supervisor comes up to you and he says, there's 2 new objects that appear in the sky. I want you to calculate them. I want you to calculate some characteristics on them. We've got alpha, we've got omega. At a specific time, you note that alpha had an altitude of 700 kilometers, and it was traveling at a specific velocity, right? And then you use a different tracking mechanism to look at omega. We know that omega has an orbital semi-major axis of 7,000 kilometers, okay? That's the difference between them. And that's all we know about the semi-major axis. It's just 7,000 kilometers. So what are the orbital energies, expressed in, again, square kilometers per square seconds, of the 2 orbits? So let's do problem A first. Problem A. We want orbital energies, and we know E is equal to V squared over 2 minus mu over R. which is also defined as negative mu over 2a, right? So let's do the energy of alpha first. The energy of alpha then is equal to velocity of alpha, which we were given this over 2, minus mu over r of alpha, or the position of alpha, where position of alpha is really just equal to this, because again, we were given the altitude of alpha, but we weren't given the position. So altitude of alpha, for your position of position of alpha is equal to the altitude of the object alpha plus the radius of the Earth. Okay, so that's how you get position alpha. And from here, you can calculate the energy of alpha. Okay, now energy omega. Let's see what information we're given on energy omega. So energy of omega has an orbital semi-major axis of 7,000 kilometers. That's the only information we're given. Okay, that's it. Well, we can go like this. We know that the energy of, that's right. The energy of omega is equal to, and we're going to use this form instead now. We're going to use this form instead because we have semi-major axis, is equal to negative mu over 2 times the semi-major axis of omega. Okay? So these are two things that we can calculate right here, the two energies. I'm not going to calculate them for you guys. If you guys want to do that, then download this worksheet and do them yourself. I'm just showing you how to get to these answers. Which has the higher or less negative energy, right? Because these are both probably going to be in a circular orbit, elliptical, rather, orbit. So B is just simple. Whichever is higher from problem A right? It's either going to be E alpha or E omega. Okay, those are the two options that you have, right? Whichever one is higher, E alpha or E omega. And let's look at problem C now. Problem C, what is the semi-major axis of object alpha? Okay, so let's look at this. All right, so C, again, I'm going to write it down again. E of alpha is equal to V of alpha squared over 2 minus mu over position vector of alpha is equal to negative mu over 2 semi-major axis of alpha. And we want the semi-major axis of alpha. Well, guess what? We can go like this. We know the energy of alpha, which was calculated in part A, is equal to negative mu over 2 semi-major axis of alpha. Well, if we just move semi-major axis over here, and if we replace it with energy, then we get the following. The semi-major axis of alpha is equal to negative mu over 2 E of alpha. And check that out. Now we have semi-major axis of alpha. So that's how you do the first problem. This is how you approach the first problem on the worksheet. This is the steps for doing A, B, and C right here. V squared over 2 minus mu over r is mu over t. So first thing, we had to calculate the energies of both. You can either use this form right here, or you can use this form right here. Those are your two options for the forms that you can use. I decided to use this form for calculating object alpha's energy, and I decided to use this form for calculating object omega's energy. And then I have the two energies, so I can just compare them to the two, and I can see which one has more orbital energy. And then C, I'm using another form, and I know the energy of alpha because we calculated energy of alpha from the first step already, and then I'm solving for semi-major axis of alpha. That's all I'm doing there. So we have semi-major axis. Okay, so that's how we do, problem 1. That's how we do problem 1 right there. So let's look at problem 2 now, okay? Problem 2. Cleaning my tablet. Okay, so problem 2. Upon doing some more research onto a third object, object beta, you've determined the object has an angular momentum vector of the following. Okay, we were given an angular momentum vector. And the first thing that we have to calculate is what is the magnitude of the angular momentum vector. Okay. The second one, what is the orbital inclination? So what's the inclination of the orbit just based off the angular momentum vector? 3, what is the semi-lattice rectum of the orbit, which is, again, a parameter that defines kind of how far you're going to shoot out from your periapsis. And we define this to, again, be p. It's the letter p for this, lowercase p. If beta is orbiting the Earth with an eccentricity of 0.2, so now we're given eccentricity, then we're going to calculate a few things, like semi-major axis, radius of periapsis, and radius of apoapsis, okay? And then I give you a ton of hints down here as to what equations to use and whatnot, but we're not going to use those. I mean, we're going to use those, but we don't need to go over them right now because I will show you in the process. So 1, what's the magnitude of the angular momentum vector? Well, to take the magnitude of the vector, the notation is this. The magnitude of a vector is equal to the x component squared plus the y component squared plus the z component squared, everything raised to the power of 1/2, which is in other terms looking like this: the square root of hx squared plus hy squared plus hz squared. So you take the magnitude of a vector, okay? Now let's look at the second problem here. What's the orbital inclination of object beta? Well, we went over how to calculate all of the orbital objects, or the orbital elements, excuse me. So we already know that inclination is equal to the inverse cosine of the z component of your angular momentum over the total magnitude of your angular momentum, okay? We already went over that, and that'll give you a value in between 0 and 180 degrees. Okay, that's what that value will provide for inclination. But we already know that from the equations that we went over in class already that this is how to solve for inclination. So let's take a look at the third problem. We see what's the semi-lattice rectum of the orbit expressed in kilometers. Well, we know this. We know the equation C, P is equal to h squared over mu, which again is just equal to the magnitude of the angular momentum vector, which we've calculated the magnitude in step 1, squared over mu of the Earth, which is provided in problem 1. Okay, we already have all that information. And then lastly, we have this. If beta is orbiting the Earth with an eccentricity of 0.2, what is beta's semi-major axis, radius of periapsis, and radius of apoapsis? So let's calculate that, right? We know A is equal to the, well, we know this. We know the following other equation for P. P is also equal to A times 1 minus E squared, right? P of beta, rather, is A of beta. I'll be consistent right here. Eccentricity of beta. We know semi-lattice rectum. We know eccentricity now. We want this right here. This is what we're solving for, right? So let's go ahead and solve for that. That looks like this. Your semi-major axis of beta is going to be equal to your semi-lattice rectum of beta divided by 1 minus eccentricity of beta squared. And you have all of this information here, right? No, Yoshiro. Inclination is technically in between. It's in between 0 and 180 degrees. That's how it's mathematically defined as an orbital element. Now you can have, right, if you really want to define. I know what you're saying, Yoshiro. What you're typically saying is this. What you're saying is that you'll typically see an orbit like this, right? Let's say that this is flat. Let's say that this is tilted upwards, your orbit right here, by 5 degrees. And let's say you have another orbit that faces this direction that's tilted down by a relative angle of -5 degrees, right? And we're just looking face on to the orbit, Yoshiro. This is absolutely correct if you're moving in this direction, okay? If you're moving in this direction right here, then this is absolutely correct. Correct. Okay? This right here is not -5 degrees. If you're moving again in this direction, right here, that's not correct. Your inclination is still 5 degrees. It's still 5 degrees. The difference is you're rotating what's called the right ascension of the ascending node. You're rotating your RAN by 180 degrees. But these inclinations are actually still just 5 degrees away from each other. Now, it's a little bit different if, let's say, you were moving in this direction. Instead, if you're moving in this direction, then this would actually be 180 degrees minus 5 degrees, or 175 degrees of inclination. And that's why inclination goes to 180 degrees. So you can account for retrograde orbits. But no, this is actually still just 5 degrees. It's still just 5 degrees. I'm going to put a question mark there. It's not the best place for a question mark. That's also not the best place, but whatever. Okay. I'm going to get rid of the question mark. But it's actually still 5 degrees. Oh, Yoshiro, I actually went over that in the notes, man. Yeah, so go over your orbital elements notes, and you'll be able to see that. But that's still 5 degrees. Nothing changed about that. So we've calculated a semi-major axis, and then we need radius of periapsis and radius of apoapsis. And then we have the following simple equations. Now that we have A, we can go like this. Radius of periapsis of beta is equal to a semi-major axis of beta times 1 minus eccentricity of beta. And then radius of apoapsis of beta is equal to semi-major axis of beta multiplied by 1 plus eccentricity of beta. Now, radioapsis and radio of periapsis. Okay? That is how to do all of the problems in the worksheet, okay? Again, I highly recommend you guys go and try and do this yourself. Go over the notes and go and try and do them yourselves. And again, I'm not going to be offended if you don't do it. I mean, we're all busy here. We're all busy, right? We've all got a crazy schedule going on. I totally get it. It's fine. But again, orbital mechanics is very important. Understanding how space and time and mass moves and operates, it's like understanding the universe. It's like understanding what you're made of. It's a lot of really neat things, okay? I ordered pizza last night. I just got a confirmation on it. That's ridiculous. But it's right. It's understanding how you move and how you react and how you operate. So it's very important to understand this stuff. Anyway, so there you go. That's how you do worksheet number 1. Okay, guys, go ahead and try this worksheet in your free time. And again, I know that free time is limited, so don't feel pressured at all. But that's how you do the first problems on the worksheet, and this is everything else you need to know for the worksheet right up above. Okay, AERO worksheet number 1. Let me make sure that this is saved. Okay, AERO worksheet. I don't know why it saved this as a smiley face. That's kind of strange. Anyway, guys, that is I think the end of what I wanted to do for today. So give me one quick second here. I'm going to make some modifications. Anyway, guys, if you have, again, I'm going to be uploading all of these notes. If you have any questions about what I'm doing here, or if you have any questions about the content, yada, 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 go ahead and just let me know, and I will do my best to compensate for that, and I will go over things for you, right? I'll go over things for you. But go ahead and try that worksheet. Go ahead and try that worksheet in your free time, okay? It's a lot of fun. I guarantee it. It's a lot of fun. Yeah. So anyway, I think that's all I'm going to do right now, guys. I've got a lot to take care of this morning, or this afternoon, rather. So I don't think I'm going to do any more. So anyway, guys, have an excellent evening. Have an excellent afternoon, whatever time it is for you. Have an excellent morning if it's morning for you. Again, I'll upload these notes for you guys so you have access to them. And yeah. So anyway, guys, thanks for hanging out. It's always a lot of fun with you guys. Again, expect a slight change, right? We're going to be going over some history concepts. Looking over the orbital mechanics maneuvers of a few different missions that have already happened, things like that, okay? We're going to go over a lot of different things, and it's going to be a lot of fun, okay? It will be, I guarantee you, a heck of a lot of fun. So, just stay in the loop, okay? Yeah. Okay, well, that's probably all I'm doing for today. So I'm signing off. Guys, have a great night. If you have any questions about this stuff, hop in the Discord. Okay, hop in the Discord and ask any questions that you want. All right, guys, have an excellent evening. Let's see if I can just hand it off to somebody else. Okay, I'm gonna hand it over to Jebs, who is playing some Kerbal Space Program right now, and he has a lot of mods. Okay, so anyway, let's go talk to Jebs, and if you're signing off, then have a good day, everybody. But I'm just gonna go and host Jebs right now. So, guys, have a great evening. Make sure I spell his name right, and I will catch you all later. Thanks for hanging out.